Hello everyone and welcome to Machine Learning Tutorials. In these tutorials we present real and applicable knowledge of machine learning. In today's video we will talk about bootstrap aggregate or bagging method for ensemble machine learning. We will explain how to implement the bagging method in Python and Scikit Learn library. This video tutorial is organized as follows. In the first part of this tutorial, I will explain the basics of the bagging method. In the second part of the tutorial, I will explain you how to implement the bagging method in Python. And finally, at the end of this tutorial, you will learn how to generate these nice graphs that you can see over here that show the classification results. Before I start, I would like to mention the following. Those of you who are my subscribers or who follow my channel know by now that I always create a post that nicely summarizes everything that I will explain in this video, and consequently, here's the post. Secondly, it took me a significant amount of time, energy, and planning to create this post and this video tutorial, and consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Okay, so let's start. Let us assume that we have a set of data samples. We call this set the original data set. Then the bagging method consists of the following steps. First of all, we create n random data sets from the original data set by using the bootstrapping method. The bootstrapping method will be explained in the sequel, so don't worry about it. Then, the second step, train a single classifier on a single data set. After this step, we have n trained classifiers that are trained on n different data sets coming from the original data set. Then, once we completed the training or fitting process, we want to make a prediction. So let's say that we are given a test sample. Then we predict the class label by aggregating the predictions of all n trained classifiers. In this step, to select the class label prediction, we use the voting strategy. Don't worry if you don't understand these three steps. I will explain them graphically in the sequel. The word bagging is forged by combining the words bootstrap and aggregating. First, we need to explain the step 1. That is, we need to explain the bootstrap approach for selecting random samples. This approach is based on random sampling with replacement, and it creates a series of data sets with the same or a smaller number of samples than the number of samples in the original data set. These data sets are called bootstrapped data sets. Let us explain this random selection process graphically. For that purpose, consider figure 1 shown over here. This is our original data set. Here, for presentation clarity, I assume that this set only contains 6 samples. The samples are denoted starting from number 1 and ending at number 6. Of course, every sample has certain features. However, here we are not interested in features. They are not relevant for our discussion. Over here, we represent our original data set in compressed form. Number 1 is the first sample, that is, it's this row of the data set. Similarly, number 3 is the third row of the data set. Next, let me explain you how to generate this data set, that is, the first bootstrapped data set. First, we draw a random sample from our original data set, and in this case, we draw number 2. Consequently, we included number 2 in bootstrapped dataset. Now, when we draw the next sample, we will also take into account number 2. This is because we sample with replacement. That is, every time we select a certain sample, we will include it in a data set. However, when we sample the next sample, we can also choose the same sample. And in that way, we generate number 3, number 1, number 2. Notice here that this is the second replica of number 2. Yes, this is perfectly okay since we sample with replacement, and consequently we select number 6 and number 4. In the same manner, we select the second bootstrap data set and the third bootstrapped data set. Okay, so that was step 1. Next, we explain step number 2. In step number 2, we train 3 classifiers by using the corresponding bootstrapped data set. We can choose a certain type of a classifier. For example, we can choose decision trees. So, classifier number 1 is a decision tree. Similarly, classifier number 2 is also decision tree, and classifier number 3 is also decision tree. Then we train classifier 1 by using the bootstrapped dataset number 1. Similarly, we train the classifier number 2 by using the second bootstrapped dataset, and we train the classifier number 3 by using the third bootstrapped dataset. Now, although these 3 classifiers belong to the same type of classifiers, that is, they are decision trees, due to the fact that they are being trained by using different data sets, most likely they will give us slightly different predictions. This is because their parameters, that is, the trained parameters, are different because they're being trained by using different data sets. And that was the second step. Finally, let us explain the third step, or the prediction step. Let us assume that a problem at hand is a binary classification problem. That is, we only have 2 classes to predict, class 1 or class 2. Let us assume that we need to predict an appropriate class label for a new sample, sample number 7. And this sample is not used for training. That is, this sample belongs to the test data set. Now, since classifier 1, classifier 2, and classifier 3 are not trained on the same data set, most likely they might give slightly different predictions. Here I illustrated this scenario. For example, classifier 1 can say, okay, so we have a sample number 7, and this sample belongs to class number 1. On the other hand, classifier 2 might say, oh, I don't agree with this prediction. My prediction tells me that this sample belongs to the class number 2. And similarly, classifier number 3 can tell you that this sample belongs to the class number 1. The bagging classifier will take these predictions into account, and it will select class 1 as the final prediction. This is because the bagging classifier uses the majority of vote strategy for selecting the final class label. It simply counts how many predictions we have for class 1. So this is class 1 and this is class 2. In this case, we have 2 predictions for the class 1 and only a single prediction for the class 2. Consequently, we select the label number 1. Next, we will explain how to implement the bagging classifier in Python by using Scikit Learn library. We will create 2 bagging classifiers. The first classifier is based on decision tree based classifier, and the second classifier is based on support vector machine based classifier. In both cases, we create 50 base classifiers. Then we train these two classifiers on the same training data set generated from the original data set. After training these classifiers, we predict their performance by using the test data set that is completely different from the training data set. We use the accuracy measure to quantify the classification prediction performance. We test the performance of the constructing bagging classifiers by using the Moon's dataset that's illustrated over here. Basically, we have two classes, Class A and Class B. As you can see over here, the samples of Class A and Class B are not linearly separable. This means that we cannot draw a straight line, for example, a line that looks like this, that will separate Class A and Class B. If the data set is linearly separable, then all the samples of Class B will be here, and all the samples of the Class A will be over here. However, this is not the case. This is why this data set is very interesting from the classification perspective. You can learn more about this data set by clicking over here and by reading the tutorial we created about scatter plots and classification problems in Python and Scikit Learn. Here is the Python code that I will explain in the sequel. First, we need to import the necessary libraries and packages. Over here, I import support vector machine classifier. Then I import decision tree classifier. Then I import bagging classifier. Then I need to import datasets. The dataset is basically a database containing different datasets that can be used to test your classification methods. Then I need to import this function called accuracy score, since we will quantify the classification performance by using the accuracy measure. Over here, I import the function called train test split. This function is used to separate the original data set into the training data set and into the test data set. Over here, I import the standard scaler. The standard scaler function is used to scale the data and to remove the mean. The data is scaled such that it has unit variance and it has zero mean. This is necessary in order to ensure the stability of the classification training process. Then we import this function called visualize classification areas from this file, functions.py. And over here I defined a function that will plot the decision region and classification samples. These codes are provided on my GitHub page, and a link to the GitHub page is given in the description below this video. Next, we create our original data set. That is, we use the function makeMoons to create x total and y total. So let's do that. And let's see x total. Here is x total. We have two columns. The columns correspond to the x and y coordinates of this figure over here. That is, every sample in this figure has x and y coordinates, although x and y coordinates are actually denoted by x1 and x2. And these are the two columns of the data set that you can see over here. So x total is the input data set containing the features and samples. That is, this row over here represents samples, and these two columns represent features. Y total are target values. And let's see Y total. So this is Y total. Obviously we have two classes, that's why we have zeros and one. Next, we split the original data set into training and test data samples. We assume that 80% of samples are train samples and 20% of samples are test samples. That's why this parameter is equal to 0.2. Next, we create a standard scalar. Here we create standard scalar object, then we fit transform xtrain. This function will basically remove the mean and scale xtrain samples such that they have unit variance. We perform the same step for xtest. So let's do that. Okay. Next, we define the bagging classifier by using the decision tree based classifier. First, we define a decision tree classifier. We use the criterion entropy and max depth is equal to none. Random state is set to a certain number in order to ensure that every time we run the code we will get similar results. Next, we define our bagging classifier. The first argument of this function, bagging classifier, is our base classifier. In our case, it's the decision tree. Number of estimators is equal to 50. That is, we have 50 base classifier. In this case over here, we have only 3 base classifiers. So going back to our code, we set max samples is equal to 0.5. This means that basically the sets, that is the bootstrap sets, have 50% of samples of the original data set. Over here, we can observe that the bootstrap data sets have the same number of samples as the original data set. However, in our case, since we are only assuming 50%, this data set will have only 3 samples, and this data set will have only 3 samples, and this data set will also have only 3 samples. Here we set bootstrap equal to true. This means that we are sampling by using the bootstrap approach, that is, we are sampling with replacements, and jobs is equal to -1, meaning that we will use all processors we have on our machine to do in parallel the training process. Similarly, we define the bagging classifier whose base classifiers are support vector machines. First, we define the base classifier, that is, our support vector machine. Next, we define the bagging classifier. We specify as the first parameter the support vector machine. Then we assume 50 base estimators, max samples of 0.5, bootstrap true, and jobs is equal to -1. That is, our bagging classifier based on support vector machine has similar parameters as the bagging classifier defined on the basis of decision trees, except for the fact that here we are using the decision tree and here we are using support vector machines. Next, we define a list of classifier tuples. That is, I define a list whose entry is a tuple. The first entry of this tuple is the name of the classifier, and you can give an arbitrary name. Here's my bagging tree, that's how I called my bagging classifier, and here's the classifier object that we defined over here. The second tuple contains the name of the support vector machine, I call it bagging SVM, and the second entry of the tuple is the object, that's our bagging classifier based on support vector machines. Next, I basically initialize a dictionary that's used to store the classification scores. And over here, in this for loop, I iterate through tuples in this list. That is, I iterate through the classifiers. To every classifier, I apply the fit method. I use the training data. To be more precise, I use the training data that's being scaled, and I use ytrain. That is, I use the output data, output training data, that is the targets. After I train my classifier, I call the predict method by taking the test data samples as inputs, and over here notice that the test data samples are scaled, and at the end I basically compute the accuracy score by comparing the true data test, that is, the output of the test data, with the output predicted by my classifier. And let's do that. Let's train our classifiers and let's see the results. Okay, so the process is quite fast, and let us see the accuracy score. Let's see what will happen. Okay, so we see that the bagging classifier based on the decision tree has the accuracy of 0.9875, and similarly the bagging classifier based on support vector machine has the accuracy of 0.9625. Both of these accuracies are quite good, and we can see that the bagging classifiers do a good job. Next, let us visualize the classification regions and classification performance. We call the previously defined function visualize classification areas, and to remind you, this function is defined in this file over here. To make this video as short as possible, I will not explain this function. This function is provided on my GitHub page, whose link is provided in the description below this video. So let us call this function twice. We specify the first classifier, that is the first bagging classifier. We specify the data sets, the train and the test data sets, and we specify the file name for saving the graphs. So let's do that. And after some time, we will obtain the results. This is not a computationally easy process. It's going to take a while to generate all the points, to create all the graphs, because in for loops we call the predict performance function many times. As the result, we obtain these two graphs. This is the performance of the bagging classifier with the support vector machine as base classifiers. The left panel corresponds to the training samples. We can see a very nice decision regions. The decision regions, in the case support vector machines, are distinguished by a smooth line, and we can see that quite well, in a very good manner, our classifier is able to separate data that's not linearly separable. However, this is the performance generated by using the training samples. The true measure of the performance is to use the test data set that's not being used for training. And we can still observe that our classifier is able to properly distinguish test samples. Let us see the performance of bagging classifier based on the decision trees. Now, notice a big difference between these two graphs. Now I will zoom out to show that, because this is very important. You can see that in the case of decision trees, we have a more rectangular regions, right? You can see rectangular regions, that is rectangular decision regions, in the case of decision trees. However, in the case of support vector machines, you can see a smoother regions. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.